Hello everyone and welcome. Today we are going to dive deep into a super important chapter for your exams, current electricity. We're going to break down all the key concepts you need to know from the absolute basics all the way to those tricky circuit problems.
So here's our game plan. We'll start with the fundamentals, like what even is current, then we'll get into the famous Ohm's law, check out what powers our circuits, and finally, we'll arm ourselves with the tools to solve even the most complicated circuit diagrams. By the end of this, you are going to have a solid roadmap for the whole topic.
Okay, let's jump right in. We got to start with the most basic question of all. What exactly is electric current?
Okay, I want you to imagine a river. The amount of water that flows past a certain point every second, that's the river's current. Well, electric current is pretty much the exact same idea. But instead of water molecules, we're talking about electric charge. So if we count up the total charge, which we call Q, that zips through a wire in a certain amount of time, T, then the current, I, is just that charge divided by the time. Simple as that. And we measure this in amps, or amps for short.
Now here's something that trips a lot of people up. We almost always talk about electrons moving in wires. And yeah, for metals, that's totally true. But the thing that's actually carrying the charge can be different depending on where you look. Take a battery, for instance. Inside that chemical soup, it's not just electrons. You've got both positive and negative ions moving around, and it's their movement that creates the current inside the battery itself. Pretty cool, right? Okay, so we've established that current is the flow of charge, but what decides how much current flows? What's the connection between the push from a battery and the actual flow we get out? Well, that brings us to one of the most fundamental laws in all of electricity.
Way back in 1828, a German physicist named Georg Simon Ohm figured out this beautifully simple rule that is honestly the foundation of almost all circuit analysis. He found that for most everyday materials, if you crank up the voltage, that electrical push, the current goes up right along with it, in a perfect, direct proportion. And they're connected by a constant that's about to become very, very important. So that constant in the V equals IR equation, that R is called resistance. The best way to think about it is like electrical friction. It's a measure of how much a material fights back against the flow of current. A material with a really high resistance is like a tiny clogged pipe for water. It makes it super hard for current to get through. And we measure resistance in units called ohms, named right after George himself, using the Greek letter omega as the symbol. Now this formula is actually super intuitive if you just think about it for a second. Resistance goes up with length, right? That makes sense. A longer wire means the poor electrons have to push through more stuff, facing more opposition along the way. But resistance decreases with area. A thicker wire is like a bigger highway, more lanes for the current to flow easily. The new symbol here, that rho, is called resistivity. Now this is the special property of the material itself. Copper has a crazy low resistivity, which is why we love it for wires, while rubber has an insanely high resistivity, which makes it a perfect insulator. So to really truly get a handle on resistance, we need to zoom in, way in. What's actually happening to the individual electrons inside that wire? Why are they facing any opposition at all? This is where it gets wild at the atomic level. When you apply a voltage, the electrons don't just shoot through the wire like a bullet. Oh no. It's much more like a frantic game of pinball. They get a little push from the electric field, accelerate for a split second, and then bam! They crash into an ion in the metal, stop, and the whole process starts over. This chaotic start and stop dance results in a very, very slow net forward movement. We call this the drift velocity, and believe it or not, it's often just a few millimeters per second. So it's these constant collisions that are the real fundamental source of resistance. Now, I know this formula looks a bit scary, but stick with me because it tells a really simple and beautiful story. It connects the resistivity we can measure in a lab to what's happening with every single electron. All it's saying is that resistivity depends on stuff like the electron's mass and charge, plus two key things about the material. N, which is how many free electrons are packed in there ready to carry current, and tau, which is the average time an electron gets to move before it smacks into an ion. See? The more free electrons you have and the longer they can go without crashing, the lower the resistivity. Okay, so we've got current, and we've got resistance fighting that current, but what's doing the actual pushing in the first place? What's the engine, or the pump, in our electrical circuit? Let's figure that out. That push is provided by something called the electromotive force, or EMF. Now, right off the bat, I have to say, this is a terrible name. Seriously, because it is not a force, it's actually a voltage. To be specific, EMF is the ideal, the maximum possible voltage a battery or power source can supply.
It's the voltage you'd measure if you just put a voltmeter on its terminals when it's not connected to anything, what we call an open circuit.
And this slide highlights a really crucial difference between the ideal world and the real world. Ideally, a 1.5-volt battery would always give you exactly 1.5 volts. But in reality, every single battery has its own tiny bit of internal resistance, which we label with a lowercase r. The moment you hook it up to a circuit and current starts flowing, a little bit of that voltage gets lost, just overcoming its own internal friction. So the actual voltage you get out at the terminals is always going to be a little less than that perfect ideal EMF.
Okay, so Ohm's law is fantastic for simple circuits. But what happens when things get messy? When you've got multiple loops and power sources all tangled up? For that, we need to level up our toolkit.
To untangle these messy circuits, we turn to two incredibly powerful rules from another brilliant German physicist, Gustav Kirchhoff. Think of these rules as your universal circuit-solving toolkit. They give us a systematic, step-by-step way to find any current or any voltage in any circuit, no matter how complicated it looks.
So, Kirchhoff's first rule, the junction rule, is honestly just common sense dressed up in physics terms. Imagine a point where a bunch of wires meet up. That's a junction. Since electric charge can't just vanish into thin air or appear out of nowhere, it means that the total amount of current flowing into that point has to be exactly equal to the total amount of current flowing out. That's it. It's all based on the fundamental idea of conservation of charge.
His second rule, the loop rule, is all about the conservation of energy. Let me give you an analogy. Imagine you're hiking on a trail that's a perfect loop. It starts and ends at the exact same spot. Over the whole hike, the total amount you climb up has to equal the total amount you go down to get back to where you started, right? A circuit loop is the same thing. If you trace any closed path, all the voltage you gain from batteries has to be perfectly canceled out by all the voltage you lose across the resistors. The net change when you get back to your starting point is zero.
Now, a classic, real-world application of these rules is this ingenious circuit called the Wheatstone Bridge. Yeah, it looks a little complicated, but it was designed for one very specific, very precise purpose: to measure an unknown resistance with incredible accuracy. The real magic of the Wheatstone Bridge happens when you get it to be balanced. This is the sweet spot where you've adjusted the known resistors just right so that the current detector in the middle, the galvanometer, reads 0. No current is flowing through that middle branch. And when that happens, a beautifully simple mathematical relationship just pops out. The ratio of the resistors on one side is exactly equal to the ratio on the other side. This means if you know 3 of the resistors, you can calculate that 4th, unknown one with ease.
All right, deep breath. We have covered a ton of ground, so let's pull everything together and do a quick fire revision of the most critical formulas you're going to need for your exams.
Okay, this slide right here, this is your toolkit. This is your cheat sheet for the whole chapter. You've got your foundation, Ohm's law, V equals IR. You've got the formula for resistance based on a material's properties. And of course, you have Kirchhoff's 2 essential rules for tackling the complex stuff. Just take a second and let these sink in. These are the equations that will get you through pretty much any problem they can throw at you.
But before we finish, there's one last very important thing to remember. We've spent a lot of time on Ohm's law, but you have to know it's not a fundamental law of the universe like gravity is. It's more like a really, really good rule of thumb that works perfectly for simple things like metal wires. Many modern electronic components, like the semiconductors inside your phone or computer, have a way more complicated relationship between voltage and current. For those advanced materials, Ohm's law simply doesn't apply.
So there you have it. From the simple definition of current, all the way to analyzing complex networks with Kirchhoff's rules, you now have a complete toolkit for current electricity. The key now is to get your hands dirty and practice applying these concepts. I really hope this explainer was helpful. Thanks so much for watching, and good luck with your studies.